So let's have an example where we actually can model a real components and accordingly simulate our circuit. So what we see here is the same example as explained in the previous model, but the difference is we are not taking the ideal voltage source, we are taking a practical voltage source. So for example, if I right click here, along with its DC value which is set to be 1 volt, I am setting its series resistance to be of 10 ohm. So I click OK. So that's how it reflects over here. R series is equal to 10 ohm. So every voltage source will practically have some internal resistance that needs to be included for accurate calculation and simulation. Similarly, for the resistor, right click here. We see that along with having its value, we can have option of having a tolerance in percentage. So I am having the 10% tolerance in the value of the register. It means the nominal value is set to be 1k, but the tolerance will allow the resistance variations from 900 ohm to 1100 ohm, so 10% plus minus. Similarly, power rating can also be given. For example, if I set 0.25 or quarter watt, that essentially tells that's the energy consumption a resistor can withstand when the current will pass through it and it will start heating up the resistance. So similar analysis for the second register R2, value is set to be 1k, tolerance is set to be 10%, and we say that it is a quarter watt resistor. That's the carbon film resistor. We also can select the register from this library where we have different value. You see here 1k, and the tolerance is set to be 1% each for these registers. So we don't need to set manually, we can select from the library. So for example, currently we are setting 10% variation, and power rating is 0.25 watts. At the label you see here, this is the net A, this is the net B, and we have done some calculations to calculate the node voltages and the current. So here we take a look, the red diagram, we see here that we can do some calculation. For example, right over here, the total current of this circuit is voltage divided by the total resistance. This is the ideal circuit where resistance are not having any tolerances and they don't have any power rating. The voltage source does not have a series internal resistance. Its resistance is nil or is set to be zero. So it's an ideal circuit. So in that case, the current was calculated to be zero point 0.5 milliampere. Same current as shown in the loop here flows through both of these resistors. Therefore, IR1, IR2 equal to I. And VR1 and VR2 are the voltage drops across these resistors R1 and R2. They are calculated with the voltage division rule or simply Ohm's law, which is the current flowing through the resistor multiplied by the value of resistors. So it is coming out to be zero point 0.5 volt each. So you see this voltage source of 1 volt was divided, the equal voltage was divided between the two resistor voltages, that is the drop across the two resistors. But what if this circuit can be modeled more accurately? It means we have a voltage source of 1 volt and we say that it has a series resistance R of value 10 ohm, and after that this point or the net, we say that the label is A, and here we have the label out. The resistor R1 and R2 both have value of 1k each as before, but this time they have a tolerance of 10%. So we basically will say that their value will vary plus minus 10%. So in this situation, the total current flowing through the circuit would be I equals to V divided by total resistance, that comes out to be 0.497 milliampere. So 0.497 milliampere, with that value we can calculate VR1 and VR2, which are the voltage drops across these two resistors, plus minus and plus minus. So they are said to be calculated at 0.497 volt each. So now we compare the total current in the ideal circuit versus the total current in the practical circuit. So total current in the ideal circuit was calculated to be zero point 0.5 milliampere, but in the practical circuit it is less, which is 0.497 milliampere. Why? Because we have included this 10 ohm resistance. And so the resistance in the circuit increases, the current in the circuit decreases, and the drops VR1 and VR2 in the ideal case they are zero point 0.5 volt each, but VR1 and VR2 in the practical case also bit less, because again you have a practical circuit here. Now VR is a voltage drop across this 10 ohm resistance R. So it is current multiplied by this value of resistor, that comes out to be 0.49 millivolt. So if we want to calculate the voltage at node A, it would be total voltage, which is 1 volt, minus the drop across this resistor R. So we'll see that that voltage will appear at node A. We already know what is the voltage at node out, which is voltage drop across R2, which is 0.497. So once that calculations have been done, let's verify if those values occur in real practice. So we have this schematic circuit right over here. Series resistance is set to be 10 ohm, and the values of resistors along with their tolerances and the power rating has been set. Let's run this simulation, and we see here that voltage at node A is not full 1 volt, rather it is 0.995 volt. The remaining, what we calculated, is the voltage drop across the series resistance of 10 ohm, which is the internal resistance of this voltage source. That little drop goes there, and therefore 1 minus that drop is the voltage appears at node A. V out is 0.49751, so which is the voltage drop across R2, and the current through resistor R1 and R2 are 0.4975 milliampere each, as we calculated, and the total current is the same but with the negative sign, that indicates the convention that we are using. It means the current delivered to the network. So let's compare these simulated values with the theoretical one. So we have put up this table here, and now if we compare the currents, what we calculated are the same. 0.497 is the total current milliampere, and IR1 and IR2 also same as what we calculate. V out is voltage drop across R2 is same, and the voltage at node A will be a total voltage minus the drop VR, which is the voltage at across the resistance R of 10 ohm. So this is how we can actually model the real components and accordingly simulate the circuit and to understand the performance. Now the impact of tolerance we will see when in actual circuit, if the component value, in this case a resistor, that varies by a certain percent, what are the impacts on the node voltages and the currents and some other parameters of the circuit performance. We'll do that analysis in next module.